Okay, just going to wrap up the section on inverses and matrix properties here with this video. This won't last very long. Yeah, basic matrix properties here. With matrices, you have a lot of the same properties that you have with real numbers, but there's a couple that you don't have. You have the associative property that basically says if you're going to add three matrices together, then you can add in any order. You can add the first two, and then add add the last two, then add the first one, or you can add the first two, then add the last one. There's also a commutative property of addition. So a plus b always equals b plus a. Now when I say this assumes that these operations are defined. When it says a plus 0, it's not talking about the number 0. 0 in terms of matrix would be a matrix that has all zeros. So for instance, this would be the 2 by 2. This would be what they're talking about as far as 0 when they're working with matrices. So if we were dealing with 2 by 2 matrices, the 0 matrix would look like this. But if you added any 2 by 2 0 matrix to that, it would just, or any 2 by 2 matrix to that 0 matrix, it would just return the matrix. And then if you add a matrix and its opposite, it would just give you a 0 matrix. And then on the multiplication property, you do have an associative property. If you want to multiply a, b, and c together, you can multiply b times c first, then multiply it by a, or you can multiply a times b and then multiply by c. Now notice there is no commutative property. You can't say that AB equals BA. But matrices, square matrices do have an identity. So, and we've already talked about what the identity matrices are. And matrices can have an inverse as long as they're square, and you multiply them together and you get a square identity matrix. Now, there's this distributive property is important to understand. A times b plus c is the same as a times b plus a times c. And that's also true with real numbers, but what's true with real numbers is you could also say that equals ba times ca, but that's not true here. If you're multiplying a sum on the left by the matrix A, then it's going to equal a times b plus a times c, but it won't equal b times a plus c times a because matrix multiplication is not commutative. Now if you multiply a sum on the right by the matrix A, then it equals b times a plus c times a, but on the flip side that wouldn't be the same as ab plus ac. Now for equations, with matrix equations, if two matrices are equal, if A equals B, then you can add the same matrix to both sides and you still have an equation. And then also if A equals B, you can multiply on the left by the matrix C on both sides and you still have an equation. And you can also multiply on the right and still have an equation. So if A equals B, then A times C equals B times C. Now you couldn't multiply on the left on one side and on the right on the other side. So you couldn't say that A times C equals C times B, because again multiplication is not commutative. So we can actually solve a matrix equation. So in these equations, each variable represents a matrix. So let's talk about the matrix equation AX equal B. If I want to solve AX equal B, you might think, well, you can just divide both sides by A to get X. But actually you can't, not with matrices. With matrices, there's no division operation. You have to actually multiply both sides by the inverse of A in order to eliminate the A. So I'm going to take the left-hand side and multiply by the inverse. Then I'm going to take the right-hand side and multiply by the inverse of A. Now, when I do that, A inverse times A is actually the identity matrix, and the identity matrix times X is just X. Now, on the right-hand side, I'm just going to bring down the expression that I have. So the solution to that equation, AX equal B, is actually X equals A inverse times B. And that's going to be important. This solution here is going to be important in an example I'm going to show you in just a minute. But let's do another equation. Let's say you have ax plus bx equals c. Well, you have a common factor of x here, but notice the x is to the right of a and to the right of b. So if you factor the x out, you have to factor it to the right using this property up here, this right distributed property. So we have to factor the x to the right. Now, once we factor the x to the right, we get a plus b here. Well, again, you can't divide by a plus b, but we can multiply by the inverse of a plus b. So I can multiply both sides by the inverse of a plus b. Now, what that does is a plus b inverse times a plus b. Since those are inverses, their product would be the identity matrix. And then the identity matrix times x is just x. And then I can just bring the right-hand side down. So in that example, x would equal a plus b inverse times c. Now, I said I was going to show you how we could use this result. And so you actually can, if you want to solve a system, you can use what's called the matrix inverse method. Now be careful, because generally when I ask students to do this, a few of them will do it, but a few of them will try to solve it by another method. But when we say use the matrix inverse method, what we're talking about is when you have a system like this, it actually can be written as a matrix equation. You can write it as the matrix equation ax equal b. Now what I mean by that is the coefficients are the matrix A. A column matrix that has the variables is the matrix X. And then the column matrix for the constants 2, negative 2, 1 is the matrix B. Well, it says that the solution to this, A times X equal B, remember we learned up here that to solve that, all you have to do to find X, which is where our variables are, is find the inverse of A and multiply it by B. So to solve this, all I need to do to get X is take the inverse of A, the inverse of the coefficient matrix, and multiply it by the matrix that has the constants. Okay? So let's see how that would work. Alright, so this is the matrix A, this is the coefficient matrix. Now I would have to find the inverse. So I actually found this inverse in an earlier example, but if you didn't have it, you'd actually have to find the inverse of this matrix A. Now the matrix B is the constants, and X, of course, is the variables. So to solve this, to find X, all I have to do is take this inverse matrix here and multiply it by these constants. So I can take this inverse and multiply it by these constants, and then when I multiply that, I'm going to get negative 6, negative 12, negative 6, negative 6, minus 7. If I add those together, I get negative 19. And then when I multiply this row, I'm going to get 2 minus 2 plus 0, which is 0. And then when I multiply this row, I'm going to get 2 plus 0 plus 1, which is 3. So therefore, I know the first entry is my x value, the second entry is my y value, and the third entry is my z value. So that's how we solve. Using the matrix inverse method. Now, this method might seem like a little bit overkill, but here's what you have to think of. This method would work. It would work exactly the same way if we changed the three constants. So suppose you had 10 systems of equations like this, where the coefficients on the left never changed, but the constants were different. Well, the good news is the answer is based on the product of the inverse. So if the coefficients never change, then this inverse would never change. So if I had another example, let's say I had the same system where the constants were 3, 2, 1, well then I could just take this same inverse and multiply it by the matrix 3, 2, 1. And then if I had another system and let's say the constants were 5, 0, 1, I could just plug in 5, 0, 1 and multiply it. So in other words, I would use the same inverse, so I wouldn't have to keep finding a new inverse each time, as long as these coefficients were always the same. So that's a case where this method would be very helpful. And that pretty much completes the section on inverses and matrix properties.